Okay, the point of this discussion is to give us some background information on solar energy so that we can use for our other discussion of solar thermal and solar PV. You can read about this part in the solar energy chapter of your book in section 3, where it talks about the nature and the availability of solar radiation. Okay, so if we imagine all of the energy coming from the sun, some of that, not all of that energy from the sun actually hits the earth. About half of it does. So when we're talking about what do you mean by how much solar energy hits the earth, we need to think about all of the places where some of it gets lost. So a lot of the solar energy ends up getting reflected back from the earth to the atmosphere, by the atmosphere or by the clouds or by the earth's surface. Some of it is absorbed by the atmosphere, but then about half of what comes into the atmosphere actually makes it to the land and the oceans. We can describe that average global irradiance, meaning the power or the rate of energy transfer from the sun to the earth, so we call that irradiance, is about 1,370 watts per square meter. So each square meter is on average receiving 1,370 joules per second of power. For sort of shorthand notation, we'll often describe that one sun's worth of energy is about a kilowatt per square meter. I want to distinguish irradiance from insolation. Insolation is the energy that's collected over a certain amount of time. So, for example, if we imagine about 1,000 watts per meter squared, that works out to be about 6 kilowatt hours per meter squared per day. We could also calculate that per year or per hour. And so both of those numbers are going to be useful, but they have sort of similar terms but are slightly different. Okay, so how much energy are we talking about here? How long does it take for the world's annual energy demand, which in 2011 was 534 exajoules, to strike the Earth's surface as solar radiation? And here we're going to focus just on the part of the Earth's surface that is land. Alrighty, so if we start with 534 exajoules, and exa is 10 to the 18th joules. Alright, and if we divide that by 1,370 watts per square meter, and now if we consider the land area of the United States, or not the United States, of the whole world, which is 148 trillion square meters, then we get that it takes about 2,633 seconds. Okay, so divide that by 60 seconds in a minute, and that works out that it takes about 43 minutes. Okay, so where did that come from? So this was the average irradiance, and this is the area of the Earth's land in square meters. Okay, so we put all that together, and we work out that in 43 minutes, every 43 minutes, enough solar energy strikes the surface of the Earth to power the entire Earth, all of the human energy needs, for an entire year. This is an almost limitless resource. Now, we're going to see that it takes some work to harness that energy, but we're talking about a lot of energy here. So where does that energy come from? The light energy from the sun, and the heat energy for that matter, are types of electromagnetic radiation. And so what that means is that the energy is carried as waves that can then strike the surface of the Earth or the surface of a solar panel. The important thing you're going to want to remember here is that the energy of the light is related to its color, which is another way of saying the wavelength of the energy. Now, the visible light is just part of the electromagnetic spectrum, but we see that the purple light has a shorter wavelength, that's the higher energy light, and the red light has a longer wavelength, that is the lower energy light. Then infrared, which is another way of saying heat, is the light that has longer wavelengths than red. So infrared heat is below red. And ultraviolet, that's what gives you a sunburn, is higher energy than violet light, above violet. If we look at the spectrum of the solar energy, we see that most of the light that hits the Earth's surface is in that visible region. A little bit of UV, but then also a lot of infrared. So a lot of that infrared is responsible for heating the Earth in addition to providing light. We can classify the light that hits the Earth's surface as either direct light, meaning it comes as a beam direct from the sun to whatever the surface is, or it can be diffuse light that has first bounced off of little particles in the air, or bounced off the clouds, or bounced off the ground. And so the direct light, if we describe how much direct light hits the Earth's surface, we can describe that as the direct normal irradiance. Direct meaning coming direct from the sun, normal meaning 90 degrees, sort of right head on. And so we'll need that when we talk about solar thermal energy. Another way we can describe how much irradiance we get is the global horizontal irradiance. So that means both the direct and the diffuse light that would hit a horizontal surface on the Earth's surface. And that's what we're going to need for the solar photovoltaics. The amount of light that hits the sun, or the type of light that hits the sun, it also depends on the time of the year, because the Earth goes around the sun, as you know, and because the Earth's axis is tilted relative to the plane that it goes around the sun. So what that means is that if you want if you have a solar panel and you want the light to hit that panel directly, you can't have it be flat on the Earth's surface. You need to tilt it. And it turns out the amount you need to tilt it is equal to the latitude. And so you see here that the latitude is really the angle of a particular point relative to the equator, down here. And that if you tilt the panel the same angle relative to the horizon, then that will allow the light rays to hit that panel dead on, 90 degrees. We also see that the amount of light and the direction that the light is coming from changes over the course of the year. So we see that in winter, the sun is sort of moving in a path across the southern part of the sky, so we want our panel angled toward the south. But it's lower, the light is lower in the sky, so that's why our days are shorter in winter. We see that the angle is higher during the summer. And that's why it's still sort of oriented toward the south, but we get more light as the sun takes a longer path across the sky. We'll also need to think about what we call the azimuth angle. And so that's going to be the angle between north and wherever the sun is. And you see that angle also changes as we go throughout the day. So here in this example, on the June 21st, the summer equinox, we see that the angle in the morning is 55 degrees, and it changes throughout the day to become 305 degrees at sunset. So we'll need to think about the tilt angle and how that changes with the seasons, and also the azimuth angle and how that changes throughout the day. Okay, so there's a ton of solar energy. How can we think about harnessing that energy? The first way we'll talk about is concentrating solar, or solar thermal, and then we'll talk about solar photovoltaics, which is the more common solar panel. What we're really not going to talk about, but you can read in your book about, is solar heating. So this is another way of using the sun's energy for things like residential hot water, or even the whole idea of designing a building so that you can use the heat from the sun in order to keep the building warmer or colder depending on the time of year and the time of day. So again, there's a ton of possibility here, and the next several discussions will relate to how we can use that energy.